Well, hello. Welcome to our last week of online lessons. Thanks for dropping in. All right, so what we're going to do is we're going to now see how circuits, the different ways you can arrange it. Now, there are infinite ways to make a circuit the wrong way, and it won't work. And there's two ways to make it work. Two styles. And one is better than the other. It's fairly safe to say one is better than the other. So, first one we're going to look at is series circuit. A series circuit is, we want the electricity to travel in a circle. It's to travel in a circle. Remember when Harry and I we made a circuit with our bodies? All right, it had to make a circle. It had to get from one end to the other end of that battery in the buzzer thing. Well, here we have this end of the battery and this end of the battery, and it needs to go around. I'm going to click everything up here for us. Now, I'm going to want to pretend, let's pretend that this is us. This is you and me. And we're going to go on a journey around the circuit. And this is $1 billion waiting for us. $1 billion right there. You and I are here. To get to that $1 billion, we're going to make that trip around to get there. It's pulling us there. See, I want to get away from you, and you want to get away from me, because we both want to get to that $1 billion, and so we're being pushed away. Get away from me, and I'm getting pushed by you and drawn by it, and so we whip around this circuit. This is our source, our voltage source. The difference between my poverty and all this wealth down here is going to drive me, as long as this there's a difference here. Now, if I have $1 billion and I don't need any more, then I'm not going to feel that draw as much. If there's nothing here and I have nothing, well, then I'm not going to feel that draw as much. But we're going to go around here. Now, in a series circuit, so circuits around, and there's two types, series and parallel. Series circuit is there's only one path. There's only one option. There's only one way for me to get to that $1 billion, and that is to make this journey. And I have to go through 3 light bulbs to do it. 3 light bulbs. And each light bulb is going to take a little bit of my energy out of me. This guy's going to demand me to do a little work. Work, remember that word? It's going to turn one form of energy into another, turn my electrical into light. This guy's going to turn some of my electrical into light. This one's going to turn some of my electrical into light. I'm going to lose current. I'm going to lose current. So my voltage is holding here. My battery is still the whatever volt battery, 1.5 volt battery, whatever it is. And then I got my current, but this is going to rob me of some of my current, rob me some of my current, rob me some of my current, because each of these offers resistance. Now, here's a couple downsides to a series circuit. Let's do it in this order. If I break any part of it, the path is broken. If I lift this switch, if I open the switch, this is closed, currently in the closed position. This is, if I lift it in the open would mean off. Off. Then I can't get to my $1 billion. If I can't get to the $1 billion, I'm not even going to travel. I'm not even going to go this far. There's no way, there's no path to get there. If this bulb breaks, it's the same thing. I can't get to the $1 billion, I'm not going to go. But what if this bulb breaks, sure, I can't get around, and what if this bulb breaks? Well, I won't get to the $1 billion. Will I light this bulb? I'm the electricity. Will I light this bulb and this bulb, and then just stop here? Will I even do part of a journey? If I can't get to the $1 billion, I'm not even going to leave. Disneyland's closed right now. You going to drive there? No, it's closed. Why even go part way? It's closed. If I was like, but I really want to eat at In-N-Out in Barstow. Okay, fine. But Disneyland's closed. Why would you even go that far? So, if any part is shut, if something's blocking me from my destination, I'm not even going to leave. So if this guy breaks, I'm not going to stop here and here and go from here to here and then stop. I'm not even going to leave. So if one part of the path is broken, the whole thing's as good as dead. The whole thing's waste. It's just a paperweight. And the second issue is with a series circuit. So series circuit, it'll work if you have everything going for you, but there's a couple downsides. First, if any part breaks, it doesn't work. And the second part is, as this guy, now let's pretend everything's working, it's on, this guy eats up some of the current. He eats up some of the current. This guy, each guy gets leftovers. They get leftover electricity. There's less current because he's used some of it. He's turned some of that electricity into light. So there's less light for this guy, less electricity for this guy, and less electricity for this guy. The difference, the battery's voltage is slowly, it's not as much push anymore. As this guy has taken some of the charge out of the equation, there's less current for this guy to play with because some of that voltage has gotten dispersed into other things. All right, so let's show you here. Now, what we have here is I've rewired, so I got a switch, and I got two outlets here, right? And the difference, the potential difference, the voltage is between these 2 points, right? And these 2 points. Now I've wired this one in series, and I've left this one in parallel. All of your house's outlets are in parallel, because it's better. We're going to learn why. But I've broken off a piece that turned this into series. Now watch, I'm going to turn it on. Oh, well, nothing's plugged in. Let's plug in that light bulb. Well, nothing went on. Well, let's plug in this other light bulb. Now it turns on. But look, if I pull out one, the other one goes off. Goes off. Why is it going off? It's going off, turning off, because this path was necessary. Now, you're going to notice two things when I do this. You can't do this at your home. Don't do this at your home. Because of the way I've wired it, it will work here. Now, I have this guy. The electricity's going to go around, and now I'm going to complete the circuit, except without a light bulb this time. I'm going to put this wire in. Look how bright it is. There's two things to notice. A, it went on. Why did it go on? Because now the path is back in play again. And now the electricity goes around, up through the light bulb, down to the light bulb, through this wire, back to that wire, and around. But also notice it's brighter. It's brighter than when I had to share. When I had to share, now it's eating up half the electricity. They're sharing, they're splitting it. Okay? But now it doesn't have to share. It gets the full meal. And the path is now put back together. It also I can go the other way. I mean, it's this, see? It's not like it was any special thing. I just need the path completed. Okay. Path is broken again. So, if your house was wired this way, that would be a problem for your house. Because think about it, if your outlet behaved like that in your house, what would happen? You'd have to have every outlet hole filled in. You want to charge your phone. Well, that plugs into one of the two sockets. But now you'd have to fill, so you plug in your phone into this one, but you'd have to have this one filled too. And not just that one outlet, the entire circuit in your whole bedroom is probably one circuit. Maybe even your sibling's bedroom right next to yours. You might have to fill every outlet hole in in both rooms. Not only do they have to be filled, they have to be on. So you'd have to have a whole bunch of phones plugged in, alarm clocks, the television's turned on, the video game thing turned on, and your ceiling fans maybe are on the same circuit, so that on as well, plus your lights. That'd be a very hard way to sleep at night. Plus you'd have everything going. Everything going. Even, you'd have to have the TV on all the time to charge your phone. And it's all sharing, it's all taking a bite out of the current. It's all taking a bite, which means your phone's going to charge slower. And your TV is going to be barely on. It probably won't even work. It's too little electricity. That's no way to run a house. So this you can do, and sometimes they make certain Christmas lights this way because it's cheaper. But when you do that, if one light bulb goes out, the whole strand might go out, and since it's cheaper, you just throw out the whole strand and then you buy a new strand. But it's all just one light bulb was the issue the entire time. So people do series sometimes. If you're wiring your own house and you're I did this. I put ceiling fans in 3 of the bedrooms, after we moved in. A client, you ever cut a hole in your ceiling, wondering if you know what you're doing? All right. Well, anyway, and there I go. I cut 3 holes in the ceilings, and now I'm starting to pull wire. There's no electricity there. I have to bring the electricity to it. But I have to sit there in my mind and go, when I bring this wire over, and then daisy chain it to the next ceiling fan, and that one to the next ceiling fan, I have to make sure I don't accidentally wire it in series. Because otherwise, all 3 ceiling fans would have to be on, and they would all be slower. The first one would get the most electricity, and then less and less. The reason why these light bulbs showed up equally bright is because it's on an alternating current, and the electrons are going back and forth, back and forth, back and forth, back and forth. And so, which one's in front? Well, this one's in front one moment, and then this one's in front the next moment. And so the electricity, if this was a battery, we would know which one got the electricity first, because that's a one circle, direct current. But alternating current goes back, forth, back, forth, back, forth. Okay. So that is series. Series. Think about the word series. What does series mean? When you have a World Series or serial killer, you can talk about that. That's the same use of the word. But the World Series is more fun to think about. The World Series is a group of games in baseball, up to 7 games. And are they all played at once at the same time? No, they're played one after another, and you progress from one game to the next game to the next game. It's in a series. And this is like game 1, game 2, game 3. The games are in a line, in a single line. And to get to the next game, you have to first go through this first game here to get to the next game. That's what this is. You can't cut when you're in a series. A serial killer kills one and then another. Doesn't do all at once. That would be a mass murder. But a serial killer, series, it's in a line. One thing after another, after another. That's what the word series means. So there's one circle. Now, when we get to parallel, there's going to be lines across. We're going to see multiple paths, multiple options, and it's going to solve all of these issues that we just saw here. Let's take a look at parallel. Now, a parallel circuit, you see parallel lines. So you draw 2 parallel lines and you make a ladder. And you can draw more rungs on your ladder, and your branches are parallel. In reality, wires are bendy all over the place and making all funny shapes. But when you draw it out, you just draw a ladder, you put your voltage source down here, and then you just start putting pieces across, your appliances across. All right. Now the nice thing about parallel, well, let's show you actually. All right, remember these light bulbs? Now, let's put it into the parallel one. Same light bulbs. It doesn't have to have that one full. I can put this one in. I don't have to, but I can. Is it going to have to divide up the electricity? No, just as bright. Did not take away or change anything about the first light bulb. Each has its own dedicated path. Neither one gets the leftovers. Neither one is the second child that gets the hand-me-down clothes from the oldest child. They both get a full blast of fresh electricity and don't have to travel through either one. It's not in a series. We're going to see how this draws out. You see, now I'm going to turn the circuit off. Well, sure. All right. Now, I dare not put this into that open socket there, because this would have gotten its own path with nothing on it. These light bulbs slow the electricity down. If I put, it completes the circuit, this light bulb, but if I put this guy instead of the light bulb, now I have the wire, just like the light bulb, but nothing to slow the electricity down. It'll blow through there super fast and melt the wire. The light bulb actually trips it up, acts like a speed bump. We're going to get to that. But you would not want to stick this into a parallel circuit. Okay. So if one part, so let's look at this picture here. 2 bulbs, electricity, here's you and me. Here is the $1 billion. I want the $1 billion. So I'm going to run around. I go, oh, here's a path to get to the $1 billion. All right, I could also do this path to the $1 billion. I tell you what, you do this path, and I'll do this path. We'll both take paths, and we'll both get to that $1 billion pretty quickly. Now, your path is shorter. Maybe I should take your path. Maybe we should both take your path and not use that path at all. And then leave this light bulb would stay off. It's not how it works. There's so many electrons rushing that some are going to say, okay, you all go that way, but if this is empty, I'm taking it. Think about when it's lunch in the cafeteria and you're buying your lunch. Does everybody just go to the first line because it's closest? It's all the same food. It doesn't matter which line you get in. It's the same food. It's going to be delicious. The hamburger. All right, it's going to be a delicious hamburger. But does everybody go to the first line? No. Some people go to the last line. But it's farther, right? Well, why would you go to the farther line? Is it going to take longer? No, because if it's emptier, it's better. So just because this is closer doesn't mean that everything takes it. Some will take the farther line, or when you walk to chapel, some of you take the farther door because it's empty. Like, why wait in line? There's $1 billion in there. They're giving forgiveness of sins. Let's get in there. All right. So if there's $1 billion, believe me, you're going to run and you're going to find, you're going to run an extra distance if it means getting in there faster. So both routes are going to be used. If this route breaks down, I can still get to the $1 billion for this one. If this one breaks down, I can still get to the $1 billion for this one. And neither gets leftovers. These batteries don't look at light bulbs as a job. They don't sit there and go, oh, I hate, it's like a speed bump, sure, but their goal is to get to here. So as it's running around, the batteries love it, is my point. If you have more light bulbs on, more wires, more routes, let's put it that way. The more routes you have, the happier the battery is, because now the current can do this one, this one, this one, this one. If they open up more lines in the cafeteria, does that make you happy or sad? If there's more doors to get into chapel, if there's more doors to get into Disneyland, it's better for you. You're going to choose whichever one is the best. You're not going to go through them all. That would be pointless. But you're going to go through the best one for you. And so the more doors, it's better for you, it's better for everybody else. All right, so parallel is the way that we try to wire things. These two pictures show the exact same thing. This one's drawn and this one was built. We have 2 light bulbs on, 1 light bulb off. Same here. Battery, battery. The goal is to get from this end of the battery to this end. This is my 2 terminals. This is my voltage, my difference. To get from here to here. Now I'd love just to jump right over to there. Just to go, boop. I'm so close. But there's no pathway. So we, or the engineer, or the whoever, is going to say, you're going to have to take this path. When we get here, it splits into 3. I can take any of the 3, and then I end up at my $1 billion. Except I can't take this one because the switch is open, which means off. It's open, it's off. I can't take this path, so we're going to go these are going to split apart, you and I, and some of us are going to go one way, some are going to go the other way, we're going to go here. Question, why not go here and then come here? Couldn't I still light this bulb? If I'm the electricity, can't I go here and then come here and light this bulb? Why would I do that? This is the $1 billion. This is the candy. This is my goal. This is my hope and my dream. There's nothing here for me. There's no pot of gold here. I want to get to here. This is my destination. This is my driving point. This was the whole voltage right here, was to get from here to here. This is the difference. There's nothing over here for me. There's no difference. So I'm going to come here and land here. So even though that this is a route, it's not a route that I want to take. There's nothing there for me. Now, if for some reason something is put over here that's desirable, then maybe this path opens up. But at this picture, with nothing drawing me here, this is the destination, this bulb stays off. So in a series circuit, let me put this picture up here. In a series circuit, if one bulb goes out, they all go out. And they'll all be dim. This is how you draw. This is how you draw it if you were like an electrical engineer. You wouldn't draw cartoons. That'd be dumb. These are batteries. A big line represents the positive. A small line represents the negative. So we have, let's zoom in here. How many batteries would this be? Big line positive, small line negative. This would be 3 batteries. 1 battery, 2 battery, 3 batteries. And then they draw the switch. Is this switch on or off? Well, it's open, so that would mean it's off. So these bulbs would be lit or unlit. They would be unlit. We wouldn't say they're burned out. No, they're just off. Burned out means they're broken. They're just off. Now, when you draw a light bulb, you draw it as a squiggly line. A squiggly line, think of it like speed bumps. That's how I think about it. Is the electricity has to go over a rumble strip. Speed bump, and it slows down the electricity a little bit more. It takes a little bit away from the current there. And they've told us that these are bulbs. This could be a refrigerator or an air conditioner. This could be a vacuum cleaner. It could be whatever you want, your phone charging. They're telling us it's bulb 1 and bulb 2, so now we know. But you would draw any resistor, any appliance. An appliance is a resistor. It resists electricity. It has a motor or something that resists it, or a filament that resists it. No matter what your appliance is, you draw it as a squiggle. And then you can label it what it is. Or you can just say it's R1, R2, which means resistor 1, resistor 2. You know it's an appliance. Let's look at a parallel circuit. I'm going to click it all up. If one bulb goes out, they all stay lit. All right, so we got two lines here. Now, here they've drawn it on its side. Let me zoom in for us here. So, we've got, how many batteries is this? Big line, little line, that'd be one battery. That'd be two batteries. That's our voltage source. The difference between those, plus and the minus. All right, now the electricity is going to flow around, and you should be able to see that it's parallel. There's more than one path. Okay? Now, here we have R1, R2, R3. They're not telling us if it's a light bulb or what. We can pretend they're light bulbs. We can pretend they're I don't know, a radio and a television and your ceiling fan. That could be whatever. You have how many routes to get around? You can go through this route, or this route. Now, watch this. If I smash this bulb here, if I shut this down, do these stay on? Yes. What you could do is you could take your pencil or your finger, and if you can draw a path all the way around without lifting it, then it's on. Now I can't, this one's off. R3, on. If I break R2, what happens to R1? Can I go around? I can take my finger all the way around, so that's still on. R3, I can take my finger all the way around, it's still on. But R2, I can't get around, this one's off. What if I cut the wire, snip, right here? Can I get around R3? No. Can R2 still happen? Yes. And R1 can still happen? Yes. What if I snip here? Or here? Doesn't matter. R1 is still good. R2? Nope, off. R3? Off. Or if I cut it here, can't get around either. It's not even going to do half a journey. Remember, if it can't get to its destination, there's nothing over here. The $1 billion is over here. It's not over here. This is the goal. So if it can't get to the goal, it's not even going to take that route. Skip that. Go this way. Okay. So you can put switches. You could put a switch here. If I put a switch here, they'd all go off. Or a switch here. They'd all go off. If I wanted to control these individually, I could put a switch here, and that would only control R1. If I could put a switch here, that would control R2, or a switch here, R3. Doesn't matter if I put it above or below. So when you're working with wires in your hands, it's the same story. You just gotta make the, you understand the drawings. It's the same thing as now it's just live in front of you there. In electrical, the wires are color coded. The black wire is the electricity that's leaving, and the white wire is the electricity that's returning. It's the hot and the common. The hot is the electricity going out, and the white wire is the electricity coming back. And then they both can electrocute you, so that's not the issue. But it just lets you know, because you have a tangle of wires up there. It's kind of nice to remember which wire was which here. So this would be your black wires, and these would be your white wires. But you can put a switch on the black or the white, technically. I'm sure there's a best practice. All right.